It's simple. A process is the operating system representation of a program during its execution. So what is a process? A process is a program in execution. And why is this so? Well, because a user program is something that is static. It is just a sequence of bytes stored in a disk or in any memory location. So when a given user asks the operating system for executing a program, the system needs to store all of the information of that execution. So we represent now the execution of this program X with some attributes. Some of these attributes are which regions of physical memory this program is using, this process is using, which files this process is accessing, which user is executing this process, which time this has started, also how many of the CPU time this process has consumed, and more. So now, assuming a general purpose system where we have many users executing, then each time a user starts a program execution, a new and also unique process is created. This idea of unique is very important, since we will see that each process has its PID, which is basically the process identifier. So when we create a new process, the kernel assigns resources to this process. Some of these are the physical memory, some slot of the CPU time, and also allows file access. Then the kernel reserves and initializes a new process data structure with dynamic information. And now we are going to see here two key concepts in operating system. The first of one is the process control block. This process control block is the process data structure. It is a data structure used by computer operating systems to store all the information about the process. Then we have here the concept of the process identifier. This is because each new process has a unique identifier. Okay, in Linux this is a number, and it is called here the PID, which is the process identifier. So that all processes that we have running in our system, each of them has its own identifier. Now, how processes are made? Well, whenever we run a program in our operating system, a new process is made. Here we have an example using Linux. Okay, here we are using also, we create here a new C programming language file. The name of this file is P1. We use here the gedit text editor. Gedit is a common text editor in Linux. This is only an example. We can use any editor we want. Once we have this file P1 and we have inserted our code, then we compile our file using here with the C compiler. So we just type here gcc. We use here the option -o to have here and to create this executable file. The name of this executable, we call it P1. Okay, this is also a name that we can choose. And then we write the code, the C code that we have created and implemented before. We perform the compilation, and after the compilation, we then decide here to run the program. So it is at this moment when we run the program, when we execute this program, is when we create a new process. Okay, when we here execute P1. Before, on the compilation, and when we also create this new file, the process P1, right, the process designed to this code is not created. So when we here execute this executable file, we create this new process. And so on this creation, all of the system calls are going to be performed by the kernel. So we are going to reserve and initialize the process control block, also reserve memory. We are going to copy the program into memory, assign CPU when it is possible, and when we finish the process, we are going to release all of the attributes that we have managed on this process. And also we are going to release the process control block data structure, CPU all the time. During periods of its execution, we can find that this process is, for instance, waiting for data from some device to be introduced, or this process can also be waiting for information from other processes. To take advantage of the hardware, we have multi-programmed systems. That is, we can have multiple active processes, and each process has its information on its own process control block, so that the operating system will only allocate CPU to the processes that we need to allocate. So the operating system classifies the processes according to what they're doing. Normally, this is called the state of the process. This state is usually managed either with a field on the process control block or by different lists or queues with the processes in a specific state. So here very important to know, each operating system defines a state graph, indicating which events generate transitions between state. So here a common state graph is, first of all, the state run. When a process is on state run, it means that this process is assigned a CPU and it is running. It is a process that has CPU assigned. Then we have the state ready. The state ready is a state where the process is ready to be run, but is waiting for a CPU to be allocated. We can also have here that the process is on the state blocked. If a process is on the state blocked, this process does not consume any CPU, and the process is blocked waiting for an input-output to finish or the arrival of an event. Finally, a process can also have and be an state zombie. This process and this state process means that the process has finished executing but has not yet disappeared from the kernel data structures. This is the common case in Linux. Linux is an operating system that has here the zombie state. So on this figure we can see a state graph example. First of all, we create a process with fork. We will study this fork and what it means in the future. Once this process is selected to run, then we go here to the run state. And from this run state, we can go to the state blocked, the state zombie, and also we can come back again to the state ready. If we come back again to the state ready, this indicates that the CPU time has finished. If we go to the state blocked, then we have an blocking input and output operation, such operations like open, read, or write. And we can also be waiting for an event or signal to arrive. If we go from the run state to the state zombie, it means that the execution of this process has ended, but this process has not yet disappeared from the kernel data structures. If we are on the state block, then we can just go again to the state ready when we end here this blocking condition. So we finish the blocking, we'll see some examples. And also some notion that is very important to keep in mind is that if a process arrives to a state zombie, there's no way to leave this state. Okay, there's no possibility here to go back again to another state if the state zombie is reached.